Imagine you are building a prosthetic arm or an exoskeleton that responds to your muscle signals. To make it work reliably, you need to calibrate a deep learning model to your specific body. But here is the catch. You can only realistically collect a handful of movement repetitions. Few samples. And in the world of deep learning, that is a guaranteed recipe for overfitting. Traditional solutions like early stopping require a validation set, which simply does not exist in a practical calibration scenario. So how do you know when your model is memorizing noise, instead of learning meaningful patterns? Recent research points to a surprisingly elegant answer. Look inside the network. Specifically at how its neurons fire. Surface electromyography, or sEMG, captures electrical activity from your muscles through electrodes placed on the skin. It is one of the most promising interfaces for non-invasive human-machine control. But sEMG data is highly individual. Muscle fiber density, electrode placement, skin impedance, and even physiological factors like age shift the signal distribution. That means a model trained on one person rarely generalizes to another. You need subject-specific calibration. The problem is that deep neural networks are data-hungry. When you are limited to just 1 or 2 repetitions per movement class, the model quickly starts memorizing those exact samples instead of learning robust, generalizable features. And because you cannot ask the user to sit down and perform a separate validation routine without breaking the user experience, classical overfitting detection falls apart. This is where a new class of memorization indicators comes in. Instead of relying on held-out data, researchers are looking at the internal activation statistics of the network itself. The focus is on ReLU, or rectified linear units, which are the standard activation function in most modern architectures. ReLU outputs the input directly if it is positive, and 0 otherwise. The activation rate is simply the fraction of times a neuron fires above 0 across a given batch. When a network is generalizing, these rates tend to follow a stable, predictable distribution. But when it starts memorizing, the activation patterns shift. Specifically, memorizing networks tend to show a noticeable drop in their mean activation rate, or MAR. The underlying mechanism is tied to how the network allocates its representational capacity. As a model overfits, it stops relying on broad, shared feature detectors and locks onto highly specific, low-frequency patterns in the training data. This causes the overall fraction of neurons firing consistently above 0 to drop. In short, a declining activation rate is a diagnostic signal that the network is drifting toward memorization rather than generalization. To test this, the researchers ran a transfer learning experiment on the Nina Pro DB2 benchmark, which contains sEMG recordings from 30 healthy subjects across 49 movement classes. They used 12 channels sampled at 2 kHz, windowed into 20 millisecond chunks with a 10-sample overlap. The model architecture is deliberately compact, a one-dimensional convolutional network designed for edge deployment. It takes a 12 by 50 input tensor, processes it through 3 1D CNN blocks with a kernel size of 5 and filter counts dropping from 256 down to 64, followed by batch normalization and ReLU. The CNN output feeds into 3 fully connected layers with widths of 1,216, 608, and 256 neurons, before a softmax output layer classifies the 49 classes. The model is trained with Atom, a fixed learning rate of 0.001, and a batch size of 64. The model is first pre-trained on 20 subjects, then fine-tuned on 10 new subjects. Here is where the experimental design gets interesting. They manipulated 2 variables to force overfitting. First, they varied the number of calibration repetitions from 1 to 4. Second, they compared 2 fine-tuning strategies. In one condition, they froze all layers except the final 2, preserving the pre-trained feature extractors. In the other, they unfroze every parameter, giving the model maximum capacity to adapt, and therefore maximum risk of overfitting. During fine-tuning, they tracked test accuracy alongside the activation statistics of the final hidden layer. Crucially, they calculated the mean activation rate, using only the first batch of 64 samples per epoch. No validation set. No extra user effort. Just pure training dynamics. The results are striking. Before calibration, the pre-trained model scored just 6.5% accuracy on unseen subjects, barely above random chance. After fine-tuning, the strategy mattered. When only the last 2 layers were trained, the model generalized well, climbing steadily on the test set. When every layer was retrained, performance collapsed. The model did not just overfit, it failed to learn meaningful representations at all. But the real insight comes from tracking MAR. After just 5 epochs, the successfully calibrated models showed a slight positive shift in activation rates, while the failing models exhibited a sharp, consistent drop. The direction and magnitude of this change cleanly separated generalizing from memorizing networks. Interestingly, even the successful models eventually showed a slight MAR decline after 50 epochs, which aligns with a widening gap between training and test accuracy. This suggests the activation rate is sensitive not just to memorization, but to the broader generalization gap. The researchers also expanded beyond MAR to look at the full distribution of activation rates, the 25th and 75th percentiles, the median, and the coefficient of variation. These metrics added granularity. The coefficient of variation, for instance, spiked during overfitting, reflecting increased variance in how neurons fired across the batch. Together, these statistics form a lightweight, real-time dashboard of model health that requires zero additional data collection. Why does this matter for edge AI and human-machine interfaces? Because it solves a fundamental deployment problem. You cannot ask a prosthetic user or exoskeleton operator to perform a separate validation routine. But you can monitor the network internal state on the fly. If MAR starts dropping, the system knows it is drifting into memorization territory. That opens the door to adaptive calibration pipelines, dynamic early stopping, selective layer freezing, or automatic regularization adjustments, all triggered by activation statistics alone. This is especially critical for resource-constrained hardware, where computational budget and user time are tightly limited. Of course, there are limitations. The absolute scale of MAR depends on the dataset, the number of classes, the sampling rate, and the architecture. This is not a universal threshold you can copy-paste across projects. It is a relative, within-experiment indicator. And while the compact CNN used here is realistic for edge hardware, we still need to see how these dynamics behave in deeper networks, with different activation functions, and across other signal modalities. Future work will need to establish more standardized reference ranges and investigate cross-domain invariances. What this research demonstrates is a powerful shift in how we monitor training. Instead of treating the network as a black box that only reveals its secrets through held-out data, we can listen to its internal rhythm. Activation rates are not just a byproduct of forward passes, they are a diagnostic signal. For sEMG decoders, and likely for many other low-sample, high-stakes applications, this could be the difference between a calibration that works and one that silently fails. If you are building adaptive AI systems, edge-deployed models, or working with constrained data regimes, keeping an eye on your activation statistics might be the simplest, most effective safety net you can implement. I will link the full paper and implementation details in the description. If you want to dive deeper into how activation dynamics are reshaping model monitoring, check out the research from the authors at the German Aerospace Center and Ruhr University, Bochum. Thanks for watching, and I will see you in the next one.